Hey there! Welcome to my channel Beyond the Graph, the place where numbers tell stories and letters make sense. Ever wondered how roller coasters get the perfect drop, or how athletes make the perfect shot? The answer lies in quadratics. Quadratic equations are everywhere, shaping the world around us in ways you might not even realize. In this video, we'll explore the fascinating history of quadratics, break down the math behind them, and show you how they're used in real-life world. Let's dive in. Quadratic equations have a rich history that spans thousands of years. It all started in ancient Babylon, around 2000 BCE. Back then, mathematicians used geometric methods to solve practical problems like dividing land and measuring crop yields. They recorded their work on clay tablets using basic forms of quadratic reasoning. Fast forward to ancient Greece, around 600 BCE, where mathematicians like Euclid visualized quadratic equations as geometric areas. This approach connected algebra and geometry in profound ways. During the Islamic Golden Age, Al-Khwarizmi, often called the father of algebra, perfected these methods. He introduced the process of completing the square, a technique still taught today. Finally, during Renaissance, European mathematicians gave us the modern quadratic formula combining symbolic algebra with geometry. This happened around 1400 CE. And today, quadratics are a cornerstone of math and science, thanks to centuries of discovery and innovation. But now, history out of the way, we can actually start learning the quadratic formula. At its core, a quadratic equation is any equation that can be written as ax squared plus bx plus c equal 0, where a, b, and c are constants and a cannot be 0. The graph of a quadratic equation is called a parabola, and it looks like this. If a is positive, the parabola opens up, like a smile. And if a is negative, it opens downwards, like a frown. And because we love graphs in this channel, if this a would be 0, we could think of it as just this part right here. Bx plus c equals 0. What would look something like this, for example. So this right here would not be a quadratic equation if this a would be 0. Now let's solve one. Let's say we have 2x squared plus, but yes, that is a, 2x squared plus 4x plus, actually, we are going to do negative or minus 6, and I'll show you how it affects the way of solving, equal 0. Now, like I said, here a is 2, b is 4, and c is 6 or minus 6. We'll figure out the 6 and its sign later. Now here, I'll just write the formula so we can plug in the numbers and that's it. Now, sorry for the small numbers, but this right here is b, this right here is b, this right here is a, this right here is c, and this right here is a. And yes, this letter right here means this letter right here. And that's pretty much the whole equation with the formula. Now let's just plug in the values. We have x equals, now this minus b is from our example 4, but here's it's plus b, and we have plus b or plus 4, but here it's minus b. So we have to change the sign to minus or negative. Now this plus minus sign here is part of the formula and it doesn't change. And so is the square root, but what is inside the square root, that's something we have to actually change. So now for the b and the square, the b is the same that we just did, it's 4, but now here there is a square. Next we have minus 4, that is a number and it's part of the formula, doesn't change. Now remember, if there is no sign in front of a letter and a number, for example here we have 2 and x, it actually just means times, like 2 times x. Or here it's 4 times a times c. So what is our a? It's 2. We do minus 4 times 2. And our c, now here is the tricky part. It's minus 6, not 6. Remember, take the sign with you. And put it in brackets, because we can't have 2 signs with each other. Now below the line we have 2 and a. 2 is number, it doesn't change, but a, again, it's 2. 2 times 2. Boom. We keep going. X equals minus 4, there's nothing to calculate. Plus minus, same thing. Square root, doesn't change. But now we have something inside the square root, and sorry, this is still going. 4 squared gives us 16. And now we have minus 4 times 2 times minus 6. We are going to calculate minus 4 and minus 6, or minus 4 times minus 6, it's 24. And remember, because we have an even amount of negative signs, we're getting a positive. And as you can see, there's even amount. We can already put a plus sign here. Like I said, 4 times 6 is 24 and times 2 is 48. We can plug in here 48. Now the line, it doesn't change, but 2 times 2, well, what is it? It's easy, 4, right? Now let's keep going here. We have x equals minus 4 plus minus doesn't change as usual. Inside the square root, actually we don't have to make that so long. 16 plus 48, we get 64. Under or over, but under the line, we have 4. We keep going. X equals minus 4 plus or minus. Now we are going to calculate it, and it's pretty simple. Square root of 64, it's just 8 over 4. Now here, this plus or minus sign changes something, because this plus and this minus actually means that we are going to get 2 actual possible solutions. So we're going to divide the plus or minus, actually not dividing the actual thing, but I'll show you. We're doing or putting 2x, because we are here going minus 4 plus 8 over 4, and here I am going x equals minus 4 minus 8 over 4. So as you can see, we have left the minus from here, and we have taken out the plus here, and we have divided it into 2 separate equations. And now we can just solve them separately. And I will keep going here, so don't worry about this thing right here. What do we have? X equals minus 4 plus 8. It's 4. So I was going to say 8. It's 4. This is 1. Then we have x equals minus 4 minus 8, and that is x equal minus 12 over 4, and that makes it minus 3. Now after all of this, we actually got two solutions, x equals 1 and x equals minus 3. So the solutions are x equal 1 and x equal minus 3, which means the parabola crosses the x-axis at these points. So here's what I just said. Imagine we have a graph, and the graph always has some values. Here we have 1, 2, and 3, so on and so forth. But we also have minus 1, minus 2, and minus 3, so on and so forth. But here is our parabola. The solutions are the points where it crosses. We have minus 3 and 1. So right here and right here. It means that the parabola looks probably something like this. And quadratics don't always have real solutions. Sometimes the value under a square root can be, for example, negative, leading to complex solutions. But that's a topic for another video. So this part right here under the square root is actually called the discriminant. Now what this means is this thing right here under the square root, if it's over 0, there is two solutions like we had. If it's 0, we only get one point where the parabola crosses the x-axis, or we call it the double point. It would look something like this. I'm sorry. Something like this. You get the idea. It touches the parabola or crosses the parabola only in one point, for example 1 here. Now if this discriminant is below 0, if it's negative, remember the parabola or the equation does not have any real solutions, so it would not touch the x-axis and it would look probably something like this. Now the boring part is over. We can talk about one of the coolest ways quadratics show up in real life: projectile motion. Imagine you're playing basketball. You take a shot and the ball arcs through the air before hopefully swishing through the hoop. That arc? It's a parabola, a perfect example of a quadratic equation in action. Here's what's happening. When you throw the ball, it moves in two directions at the same time. Horizontally, where it keeps moving forward at steady speed. And two, vertically, where gravity pulls it downwards, causing its height to change. The combination of these two motions create the curved path we see. Mathematically, we can describe the ball's height with a quadratic equation. This right here is function, and we read it as h of t equals minus half gt squared plus v naught t plus h naught. I'm sorry, really genuine mistake. Remember, if you're a mathematician, type your t's like this so you don't mistake them to plus signs. Where g is gravity, v naught is how fast you threw the ball upward. H naught is the height you threw it from. For example, let's say you threw the ball from 2 meters high with upward speed of 10 meters per second. The equation becomes h of t equals minus 4.9 t squared plus 10 t plus 2. And everything here actually makes sense. For you non-physicists here, let me explain everything. This age of t is just a way to name. This minus 4.9 comes from the original equation or function, where the t is just a time, the squared is part of the function, and because if it's minus and it's squared, it becomes a frown parabola. This 10 right here was just the upward speed. And this plus 2 is just a constant, is like where we start, from here. And now if I would graph it, I would start from the constant. The constant is 2. It means where it's passing the y-axis. For example, here it's 2 is probably around here if 1 is here. And it's starting from here and it's going up and coming down. And it keeps going, but we only have to think about this. So this was not accurate curve, but this is more like it. So the highest point happens when the upward motion slows down, just before gravity pulls it back down, like this. The ball eventually comes back to ground, and the quadratic equation helps us figure out exactly when and where that happens. So you could calculate the t using the formula for a random point. Let's say we have point here. We could calculate the t and plug in this value right here to get the time, how long it is in air before reaching this point right here. Even if you're not solving the math yourself, quadratics are at work every time you see something fly through the air. Whether it's basketball, a frisbee, or even a rocket. Pretty cool, right? And that was it. If you want to see more about physics, just let me know in the comments. And if you did like the video and subscribe, because I want to make this for you and you can choose what do I make next. Thanks for watching, and we'll be back next time.